both in standards and in extending those standards, talking about protection, real-time monitoring, centralized management, and ending with an application that was just launched last year in the UK. So for some time now, we've seen that IP for contribution media is mostly used for long-distance transport. In fact, we have some applications where we have pretty complex distribution of content over a mesh-type network or long-distance networks. What we are seeing is that they are gaining some acceptance into extension of production facilities, right? So why do we see a lot of these effects coming is that, well, of course, bandwidth cost is dropping. It's true for compressed video over 1 over gigabit Ethernet. That's been growing strongly for many years now. But video over 10G right now is being deployed. And when I say 10G, we're talking about 702022-6 uncompressed SDI over 10 gigabit Ethernet. In fact, a couple of months ago when gigabit Ethernet links over diverse paths from India all the way into the UK itself. So we're seeing a lot more of this kind of applications growing. One of the key factors, of course, is our infrastructure extension. It's much easier to share and collaborate if you have media and both data over a wide area network. And in terms of applications, one of the applications that we've seen today is, for example, the PAC-12. So PAC-12 has now started to use what they call IP production. And what they're doing is they're deploying fly-away kits into the venues and bring all the content from all the different venues and matches back into the San Francisco production facilities. What they have told us is that they're running about 800 venue events a year, sometimes simultaneous, up to 3 events per day, at a cost savings of approximately $10,000 per event. That's going from a large OB event to a small event for on-site support. All this is possible because of standardization. There's really no need for proprietary systems today. Of course, there are some things that need to be done to bring 2022-6 or -1 or -2 or -7 to be more efficient, but it is a standard and it has helped us to deploy many systems today. And I think more importantly is that the requirements for IP media transport is better understood today. In the past, it's pretty much black art. You launch your content into the network, you're never sure whether it's going to get there. But today, there are so many things that we can do to guarantee the quality of service, the quality of engineering. That is so much easier to ensure that you have very high quality of service. So I guess what we really want to do is how can we increase and accelerate acceptance of deployment of video or media over IP. And what we feel is that there's 3 primary things that we need to take care of. First is reliability. We need to protect and monitor media in real time, and in order to ensure that content gets delivered and in a timely fashion. And also, if there's a fault, how do we actually trace down the faults in a very complicated mesh network, for example? The other thing what we need to do is to increase the familiarity, right? So from a broadcast transport perspective, within the facility, you're very much used to control panels, push buttons to actually run salvos or to make connections. How can we extend that without changing that user interface, but switch out the facility, the infrastructure, or go through a hybrid transition from a baseband to an IP network? So what we need to do is really increase that kind of familiarity. The third is to prevent disruption. So disruption can come in many forms. There could be the fact that someone might pull off an Ethernet cable or a fiber link, and you lose content immediately. But what if someone also puts in content into your network? In the past, if you plug in an SDI video interface into your router, for example, it's not really getting switched to any location. But if you put IP content in the network, you have really no idea how it's going to actually interfere with your packet transmission. So what we need is ability to build infrastructure that has very deterministic behavior. Basically, to take the flexibility of IP, but make it somewhat static like a broadcast network. So the three things that we need to talk about, of course, is based on that build-up is resiliency. How can we actually leverage and extend protection mechanisms that is available today in standards to actually provide even more protection for our high-value content, to apply techniques in monitoring, to provide target fault finding, so that if you have a fault somewhere in the network, you're not dependent on a video monitor at the destination to try to troubleshoot. That's really impossible in these networks today. And the last thing that actually binds it together is centralized management. If you were to shorten that, what it really means is SDN type infrastructure for video transport or software-defined networking. So for media protection, so of course everything that we do today, hopefully is standards-based. We're trying to get away from the proprietary nature of legacy video networks, for example. Forward error correction is a published standard. We can use it. The problem is that it's really built for very short losses or packet losses. And in most cases, if you look within the facility itself, it's more a fault if a link of a node brings down the entire circuit. So it's a little bit of insurance. It doesn't really help if you have long burst loss or a loss of a link. So in 2012, was it 2013? 2022-7 was released, providing seamless switching. So there's already discussions about it today. It provides the highest level of protection at the cost of double the bandwidth. All right. Now, if we look at resiliency and protecting media over IP, there's many methods of extending the standards that we have today. For forward error correction, if let's say you need to go around it over a long distance network, the simplest method is to increase the forward error correction matrix size itself to make it more robust to long runs of packet losses. Of course, the flip side of it is that it increases latency. With regards to RTP switching, what we can demonstrate or have been able to demonstrate is that with enhanced designs, you can actually select packets from any of the diverse paths. So this really acts in itself as 100% forward error correction. To extend RTP switching, what we can build on top of it is the concept of hardware redundancy, or 1+1 redundancy, for both the transmission side and the reception side. So not only are you protecting for link failures or node failures within the infrastructure itself, on the network itself, you can actually build systems that are actually highly redundant in the immediate adaptation layer. So earlier on, 2022-7 was brought up as a highly resilient method of protecting media. So how does it actually work? This is a little graphic that shows that with every single media input into a media adapter, what we essentially provide is dual stream outputs. So the payload itself is absolutely identical. So the only difference here is the Ethernet frame, the IP addresses, the UDP ports. This can be supported in unicast and unicast, unicast and multicast, in any which way you want to transmit into the network. So when a fault occurs, of course, you basically lose a link. And what happens is that the receiver continuously buffers and looks at the incoming streams and makes a seamless switch. And when we talk about seamless switching, it's a non-detectable event. And so this is applicable for whether the content is uncompressed or compressed. Now, the standard itself doesn't talk about how much buffering you need to do or what kind of switchover that you should actually implement. Depending on how you design the systems, you can actually make it very intelligent to the point that you're selecting it on a packet-by-packet comparison basis between the two paths. And by proper comparison, you can actually even protect for outlier cases where you have alternate packets dropping on either link. Right, so this gives you very, very robust type protection. So how can we extend this? So we have the concept of what we call encoder partner protection, or essentially 1+1 hardware redundancy for RTP switching. And what we have is that the media is actually transmitted from the master media adapter along a primary path, and then on the secondary path is actually forwarded to a slave adapter that automatically forwards that output. So there are two methods in running these systems. This EPP protection, or the link between the primary and the primary and the slave, and the master and the slave. This link is actually just an Ethernet link. So one of the really cool things about this is that we can actually provide such protection over very or highly geographically diverse networks. So one of the applications for this today is actually in radio contribution in the UK with the BBC. And what they have is a primary site and a disaster recovery site that's separated by 100 kilometers. So they can actually do perfect switching in the case where there is a link failure. You get that RTP perfect switching behavior. And in this type of configurations, what you can do is that you can actually protect for hardware protection. Protect for hardware faults. So if your primary fails, your secondary or your slave automatically forwards the packets into the network itself. So with this kind of protection schemes, you can actually provide extremely robust content or media delivery over any type of IP network. So that's for the transmission side. And on the receiver side, you can do the exact same thing by duplicating the setup here. So you have multiple receivers independently receiving from the primary or the master and the slave streams, giving you the protection switching. So for media monitoring, I think it's relatively true that monitoring is typically an afterthought. We tend to spend a lot more on the hardware infrastructure and transport itself rather than on the monitoring itself. And to us, monitoring must be approached from a holistic perspective. You have to look at the entire network in its entirety. This is no longer the same thing as looking at a multi-viewer output from a video router, for example. If that video fails, in the past, you could trace it down relatively quickly. But with multiple streams, with competing data over an Ethernet network, actually trying to trace down a fault becomes incredibly difficult. So there is lots of guidance available for real-time monitoring. You can look for SAMP standards for SDI, ITU 1541 for network performance metrics, 101.290 for transport stream monitoring. But measurement of all points in the transmission chain provides the ability to quickly diagnose faults. And that is, if your focus was really trying to determine where the fault is, this is the best way of doing it. The problem is that it leads to information overload, right? There's too many parameters and too many streams and circuits, too many hardware elements to actually try to figure out where the fault occurs. So what we actually advocate is the concept of correlation. It's very important to not only monitor the points and alarms associated, all the parameters and alarms in the network itself, but look at these parameters and alarms and associate it to a specific service. So if you have a fault that occurs automatically, a fault that occurs in the network, the system will be able to automatically point out where that fault occurs and where you need to go in order to troubleshoot that fault itself. So from a media service monitoring perspective, we believe that, the best case is to provide monitoring at all locations. That includes monitoring at the source itself, monitoring at the media adaptation layer, monitoring at the Ethernet layer, even the baseband layer of video routers. So once you have monitored all these alarms for all these parameters, you can monitor the connection layers, the connections itself, in a logical layer. And within this logical layer, you can associate it with a service. And once you can associate this service, you can actually start providing analytics to provide QoS, QoE scores, whether you actually have met your SLA compliance, and even to look at usage patterns. Because as you build your network, there will reach a point where you come up close to capacity by looking at the network itself and how it's actually being used today, or in the future, you can actually plan for maintenance, plan for downtime, plan for upgrades, so on and so forth. So there was a discussion about how we can actually provide salient data for user-friendly fault finding, right? So if today I had a loss of video in the Ethernet mesh network, I look at my video output, it's gone. What am I supposed to do? You can use SNMP. It reports all the faults, but then you have to parse through everything and say, where is the fault actually? So what we strongly advocate is to build highly application-specific views so that you can actually look at all your content, whether it's thumbnails, circuit behavior, link load, link or bandwidth utilization, and actually when a fault occurs, automatically backfill to tell you where that fault occurs within the network. And in this case, we use metrics like EDHCRC, packet loss, TR11290 metrics. We can actually look at packet delay variation, packet loss ratios, so on and so forth. So the goal ultimately is to provide that sense of security. So what we feel is that a highly integrated system with a higher level monitoring system that pulls in all the data, aggregates the information, analyzes all the data, and presents a resolution for fault finding is very, very important. So the third piece of this is simplifying the complex. Software-defined networks, of course, is a buzzword right now. But if you were to summarize it and to filter it, essentially what it is just centralized management. How do we actually provide centralized management or control over your entire network to guarantee QoS? So if you look at baseband versus IP, so baseband systems are typically locked down and not dynamic. They're highly static environments. The flip side of that is that it's very reassuring. I look at a single coax, I actually know what kind of content or what video I'm actually supposed to be receiving on that system. IP systems, by definition, are dynamic. Individual nodes make its own decisions automatically. So this provides a very highly flexible environment, but there's great potential for confusion. And of course, it's non-deterministic and insecure if you were to just launch packets in the network itself. If you look at traditional broadcast infrastructure, what we have is that you have a bunch of sources, a mesh network with perhaps video routers or E-to-OD converters with timelines in between. You have a bunch of destinations and a control panel or a network management system that helps you make connections. So today, a user would essentially create a connection, and that information is fed to a controller, which ultimately goes into the system and starts configuring every single element itself, whether it's a baseband router or some kind of E-to-OD converter. So this gives you the ability to route traffic from any point to any point, essentially timeline management. And it's a very good example of how systems provide traffic engineering from a broadcast perspective. If we look at Ethernet networks, or whether it's layer 2 IP or IP networks, conceptually, we can actually build on it and come to the same resolution that this can also be done from an Ethernet perspective through the use of centralized IP routing. And so what we have is essentially the same video sources, the same destinations, a control panel or network or just a client or terminal to make connections. But in between, what we have is perhaps media adapters and Ethernet switches in the network itself. And it all boils down to the same thing. Instead of controlling video routers, right now we are controlling switches, and we can actually build point-to-point connections, whether it's unicast or multicast. Now, why we believe that this is that OpenFlow is, or some kind of centralized management is absolutely important, is because if you were to build a mesh network like this with multiple connections between the switches, the running spanning tree on the systems like that will start to eliminate possible paths, possible links. What we have done in our systems is that we essentially turn off spanning tree, and we forward packets according to a shortest path algorithm that we store within our database itself. So every time a user makes a connection from the transmission side to the reception side, we actually automatically calculate all the possible paths and make the connection or provision the connection based on the least cost factor, whether it's the shortest path, link utilization, bandwidth availability, codecs, so on and so forth. So if you look at an Ethernet switch network, the traditional approach for configuring paths on network switches, there are two basic ways to do it. One is CLI-based. So CLI-based is basically when you go into the network, into the switches itself, and force configurations on the switches. One of the ways that we've done deterministic switching through the network is to use the concept of VLAN trunking. So every media is associated with a specific VLAN, and we tag those packets and route those packets from port to port in a specific VLAN. That supports unicast or one-to-many multicast type configuration. The problem is that it's extremely slow. Every config that you push into a switch itself takes time, because the switch, through its operating system, will actually look at it and say, is the configuration being pushed to me or that they are trying to commit, is it accurate? Are there any faults? And this can take multi-second operation. So in some of our applications, that configuration change actually takes up to 4 seconds before that configuration is actually takes hold in the switch itself. You could let it free run. In the second approach, use protocol-based networking. Automatically send the content into the network itself and let the network route. So perhaps IGMP, for example, for doing multicast transmission. It is automated and it's relatively speedy. The problem is that it depends on the network infrastructure itself and how your packets are actually going through a network. It may actually cause some bandwidth loading issues. So this is where we believe SDN or software-defined networks come into play. So this graphic has been shown already today. And what it does is essentially separates the network control from the forwarding plane. So we are taking the autonomous behavior away from the switch. We're telling the switch that, hey, you don't make your decisions yourself today. I will tell you exactly how you're supposed to forward those packets when you receive those packets. The application can control so essentially what we can do is we can provide applications that control the network via various types of API. It's open standards-based, it's essentially vendor neutral, and it gives us the ability for packet inspection and modification. So for example, when you receive a packet with this IP address, replicate it and send it to 3 or 4 different destinations. So key to this is OpenFlow. So very quickly, what it does is it provides a standardized method of actually controlling the switches directly. And actually, with the correct control, it allows us to actually interact with the forwarding plane directly to write in routing tables so that when the switch receives a packet, compares it. If it doesn't pass it doesn't match what is received, it drops it. If it does, it forwards it. So one of the key benefits from using OpenFlow is actually direct access to switch forwarding. Right? That means less time spent in configuration checks and commits. How does that translate to real life? As I was saying earlier, if you do CLI configurations, it can take 4 seconds or multi-seconds to actually commit the change into the switch itself. What we're seeing with OpenFlow is that the first packet actually exits or starts getting forwarded in about 5 milliseconds. So we are talking about 4 seconds down to a couple of milliseconds in terms of packet forwarding. Now, there are many other advantages. One key advantage is that it provides us auto-discovery of nodes and links. What does it allow us to do? So if you subscribe to the concept of using top-of-rack switches, non-modular switches, so top-of-rack switches that are 1 RU, perhaps 48 10 gigabit Ethernet ports with 6 40 gig ports, you can start building your network very small, and you can start scaling it large, but because every time you add a switch and you put it under OpenFlow control, the controller actually detects what's been added. And that also applies to links. So when you start adding links into the network itself, it starts looking at it, it sees it, and once it's once it sees that it exists, it can start using it to forward traffic. The really cool thing about this is because what we are doing is actually forwarding based on MAC addresses. You don't really have to have very complex drivers for different elements in your network. Every system in your network could be forwarding to a specific multicast address for transmission, and a reception itself could be receiving from that. But within the OpenFlow infrastructure itself, we actually forward those packets based on the source of that stream. So with packet inspection, provides matching and modification for very highly flexible processing. So there's a concept of writing routing tables into the switch itself. And with OpenFlow 1.3 and onwards, you're actually allowed to have multiple routing tables in the system. You can say that a packet comes in, I'll inspect it with my first routing table. If it passes, it gets forwarded to the second routing table, which makes a decision based on that, so on and so on and so forth. So you can make very complex decisions if there's a need to make those decisions. In such a network, what you also get is automatic access control. You actually have access control of the switches itself. So every port that is used today will be enabled. If it's under control of the system, if it's not in use, we automatically disable it. And because we use MAC address inspection and matching, any element forwarding packets or into a network in the first place onto an unused port will not be forwarded because it's disabled. That's the first thing. And the second thing, if you unplug a live system and plug it back in, the MAC addresses changes, we start forwarding it automatically. So you don't really allow unauthorized systems into the network. And because everything is minutely controlled, that means once you build a path into the system and someone goes in and disables an IP port, for example, on your media adapter, the management system will actually go in and say, hey, that's a change, that's not allowed. I'm going to override it and enforce my known state. So what this means is that even if someone accidentally makes mistakes and starts manually configuring systems that they shouldn't, the network control system or management system will actually go in and enforce the original configuration. Okay, so how is it used today? This is just one example, and this is a collaboration between ourselves, British Telecom and ITV, or Independent Television, and building a national IP broadcast network. So this is primarily a remote production type extension of their facilities. So what BT did is build a nationwide IP contribution network for independent television. The original requirement was 16 main studios and about 40 remote facilities. And what they use is BT used their next generation global media network, which had the ability to do 10 gigabit wavelength transmission with layer 2 Ethernet, and also over the Metro Ethernet MPLS network. So what they did was they ran uncompressed SDI over 10 gig Ethernet, and with gigabit Ethernet, they ran JPEG 2000. So resilience was was highly important in this application. So what they actually provided was 2 data centers for very high resiliency in London itself. And to it all, what they did was they provided that centralized management to enable ITV to go in and make those connections themselves. So ITV, in a sense, would actually have access to the network from a physical perspective by transmitting content, but they could also go in and build those circuits whenever they needed to build or make connections. So as you can see, the network is essentially a dual star topology. So every single site is more or less connected to the east and west data center. And all the critical sites are actually connected by 10 gigabit Ethernet wavelengths, and the selected regional sites are connected via gigabit Ethernet with JPEG 2000. It's a little bit of a misnomer. Really, the definition of a critical site and a selected regional site is the capability to pay for services, right? So all the larger studios will be able to purchase 10 gigabit Ethernet services for uncompressed transport, while the ones that can't afford uncompressed will actually use JPEG 2000 instead. So at the premise itself, at the customer side, the first thing that BT always does is monitoring. So when ITV handed off a baseband video signal to them, what they do is they actually have an SDI monitor that looks at the input signal itself. So at points of handoff, whether it's reception or transmission, they'll always monitor the SDI inputs to guarantee or to show that they have met their SLAs. So what we have here is that, for example, in Site 1, we go from SDI monitoring right at the bottom to 2022-6 media adapters for conversion of SDHD into 10 gigabit Ethernet and into a top-of-rack Ethernet switch. So that top-of-rack Ethernet switch is essentially a Juniper EX4500. It's a 2RU 48 10 gig port switch, and it's directly connected into the DWDM network itself. At the core itself, instead of using top-of-rack switches, what they have is the EX 8000 series. It's modular switches, so they can actually add blades whenever they needed more throughput. But everything else is exactly the same. They have 2022-6 converters for uncompressed. They have JPEG 2000 encoders and decoders also at the core itself. They pass it off into a video router, and then finally into an SDI baseband monitoring system. So one of the key requirements was resiliency. So this is where they actually built what they felt was the most resilient network that they could build at that time. All right. So what it is that at every single location that could pay for it, they actually have dual media adapters connected in a 1+1 configuration over a primary and a secondary link. And this is again Ethernet. It's called a cross strap, feeding two top-of-rack switches that is cross-fed to the two data centers. So if you look at the path for the network itself, any video content going into the system itself is guaranteed multiple paths into a receive location. So you can have failures in the in the media adapter, in the top-of-rack switch, in the links between them, in a complete failure of a data center, and you will still get your content all the way where it needs to go. So, of course, BT is not going to build a once-off network, right? So this, to them, is a multi-tenanted environment. Once they've laid the foundation of it, well, what they want to do is to be able to sell services to multiple broadcasters, customers, wherever they can. This is a truly a multi-tenanted environment, and ITV actually has access control with user profiles limiting visibility. So what happens is that within ITV itself, there's multiple user profiles. They log in the system, and they only see their own ITV network and maybe about 10, 15, 20% of the actual network itself. Within ITV, there are different groups. So you have operational groups, engineering groups, so on and so forth. And you have, for example, network administrators that have access to every single element, but day-to-day users may only be able to see certain elements, and they cannot actually configure the underlying management software itself. One of the requirements brought back from ITV into BT was they need to be able to provision services anytime with up to 30 concurrent users. So up to 30 users can log in the system over their over their national network and build connections on the fly. And there must be a minimum of 30 bookings per day. So what this means is that these 30 concurrent users making 30 bookings a day, once they made a booking or reservation, the circuit must come up or go down as required. So there must not be a fault where someone makes a connection and it doesn't really come up. So in our test with the system today, what we've seen is that they've blown past that limit. They've gone up to 50 concurrent users and almost up to 100 connections a day. And it's possible really because it encourages people to use it because it's a very easy user interface. So what you have is basically an input side, input panel, an output panel, a profile, a date and time, and essentially a connect button. So all end users would do is come in, log in, select my input to one or multiple outputs, hit a profile, and hit connect. So they can send build connections immediately. So the key attributes of the system is that this is a centralized connection management system. So everything is controlled by actually redundant servers with high availability. Non-specialists can come into the system itself and make connections on the fly. So they don't really have to have expert users on site to make connections based on a specific schedule. The connections are provisioned virtually instantly relative to the minimum of 5 minutes or more previously. So someone has an expert in the past who have to make connections, and it will take connections up to 5 minutes to come up. So now it takes 4 seconds or less to actually see your video flowing. So media is shared in real time between any location, and this is possible for even between uncompressed and compressed sites. The system automatically routes the traffic such that it gets sent from an uncompressed location into the core. And if it needs to go to a regional site, re-encodes in J2K, sends it to the regional site, and is decoded on the fly. If you look at the original network, it was an all MPEG-2 type system. So the latency was about 600 milliseconds end to end. What we have been able to deliver is that uncompressed content takes roughly about 5 milliseconds today between two of the closest locations. And with JPEG 2000, it's less than 100 milliseconds for transmission. So what they have basically built is a very resilient media transport network that actually takes high-value content through a national network. And that's it. That's all I had.